So first, I'd like to thank Chameleon Cloud for allowing me to use their HPC cloud computing infrastructure. All of the systems that we're going to be running on are going to be going through Chameleon Cloud. Chameleon Cloud is a collection of universities and HPC centers that provide some allocations for people that are working on open science. In particular, people that have ideas on how to leverage science and education in HPC. So we requested an allocation with them. They approve our allocation, and this is the one that we are going to be using. I also want to give a shout out to Aurelio Vivas because he really helped me set up all the clusters. So every single one aspect that you're gonna see in the Jupyter notebook, there is a lot of infrastructure that has to be set behind the scene in order to make this happen. So thank you very much, Aurelio, for your help. Okay, so this first section is not going to be focusing on offloading. It's going to be focusing on how do we really approach parallel programming and what are the different elements and aspects that we need to understand when we do parallel programming. So it's going to be giving a really brief introduction of why OpenMP and what is OpenMP. It's going to be giving a really brief introduction of what is a thread, what does it mean to do multi-threading, and I know you hear that word a lot, but sometimes we talk about multi-threading from the perspective of hardware. So when we buy systems, they say, oh, this comes with like 16 threads or 32 threads or things like that. But then there is also a concept of thread on software that is when we run the operating system, we're going to see later on that we actually run a lot of threads and that all of those threads have to be mapped to the hardware threads. Then we're going to talk about memory. Memory is a really big aspect of OpenMP. OpenMP is mainly a programming model that understands that memory can be shared in between the different workers in comparison with other models like MPI that will understand that workers have to communicate actively and explicitly communicate with each other, sending messages. We're going to explain the OpenMP syntax, and we're going to explain how, more or less, how the implementations actually take OpenMP and try to map it into what we actually run and execute under the hood. Okay, so OpenMP pretty much tries to answer the question, how do we parallel heterogeneous systems? Sorry, how do we program parallel and heterogeneous systems, right? So we have these new computers. These computers have many cores, they have many threads, and we have this other new set of systems that have GPUs. Then we need to find a way to explicitly define the program in some language that allows us to map our program to those systems. So one thing that is important here is that OpenMP is not a programming language itself. OpenMP is an extension of already existing programming languages, in particular an extension to C, C++, and Fortran. What we do in OpenMP is we are annotating the code that is written in one of these programming languages, and we are telling the compiler to please add all this infrastructure around our code to be able to execute that code in parallel or to be able to execute that code in a GPU. So it allows us to express parallelism, it allows us to express workload distribution, it allows us to express where in the system we are going to be running different parts of the code. So it is a standard that has been around for over 24 years. It was first introduced by the late 1990s, and it has been constantly evolving to try to adapt to different methods and to the different architectures that we see in the parallel computer systems, and in particular in the HPC area, because in HPC what we see is that we want to have massive amount of computation, and the best way that we have been able to do that is through the use of parallelism, and in particular to the use of GPUs and accelerators during the last decade or so. And so the OpenMP ARB, which is the Architecture Review Board, is a set of people that just sits multiple times a year and decides what is going to be added next into the OpenMP. So when we talk about OpenMP as a standard, we are talking about the ARB, which is the set of people that define the standard. They are people working from different industries. We have Intel, we have national laboratories like Argonne, we have AMD, we have Cray, NVIDIA, I mean, you name it. And the idea is that based on the needs of the applications and based on the experiences of each of these participants, they want to make sure that the standard has the capacity to express the different programs and to express the different parallelism schemes that the users want. Okay, so it is possible to influence the standard, especially there are two main moments that when you can do that. One of them is called the IWOMP, the International Workshop on OpenMP, which is a conference where most likely you're going to see most of the OpenMP ARB. The IWOMP conference is usually held 1 week before one of the face-to-face of the ARB. So people in the ARB usually go to the IWOMP conference and try to understand what are those things that users are doing, as well as what are those things that research people are doing in terms of OpenMP. The other one is called the OpenMP Con, which is a conference that is a little bit more open, less research-oriented, more talk-oriented, where you can just say, hey, I want to speak about this, I want to bring up this issue, or I want to say this is what I'm doing, but it's not something that you will end up publishing somewhere, right? So you can always try to use these mechanisms to try to communicate with them, and they are often really open to new ideas. Okay, so what is actually the evolution of OpenMP during these 24 years? We started with OpenMP in 1990, and back in 1990, the idea of having parallelism within a system was really not there, right? So I don't know, probably not many of you remember the Intel architectures back in the 1990s. One of the latest one that was sequential was the Pentium 4 architecture. And the problem there was that the ideas on how we were gaining more and more computational power back in the days was to increase the frequency of the processor such that we would be able to execute more instructions faster, or increase the capacity of the processor by including some architectural optimizations that will increase how many instructions per cycle were executed in the processor, right? But this made the cores really, really big, and this made the power consumption of those cores actually really expensive. And it got to a point where it was impossible to keep up with the trend of increasing the size of the processors, increasing the frequency, because it was not possible to really cool down those systems. So at the beginning of the 2000s, we start seeing a shift toward parallelism, where the single core architectures start becoming multi-core architectures. So we have the Core 2 Duo, we have the AMD multi-core architectures back in the day. So we start seeing that all the beginning of the 2000, all the way into 2010, and still to these days, we are seeing that the number of cores and the number of threads that architectures can actually have is actually increasing over and over. By the way, if at any point you have any question, comments, concern, feel free to interrupt me, say whatever you need. I'm here for you, okay? So then later on in the 2005, from the beginning of 2005, some people were starting to experiment with the idea of using GPUs. So as you know, GPUs are graphic processing units, and you know them really well from gaming. But what some people realized was that because these architectures were really good at producing pixels, they were really good at doing certain operations in a really parallel manner. In particular, matrix multiplication operations, general matrix multiplication, or alike, where everyone was pretty much doing the same, which we'll see later on a little bit more of that. So there are two trends that go out from there. In 2013, we see that the OpenMP standard started opening up the door for device offloading. And in 2008, we see that the OpenMP 3.0 standard focuses a little bit more on tasking or different strategies to provide parallelism in the CPU. We are not going to be touching tasking. We want to be able to focus on the GPU part. The idea of this tutorial, which is the first time that we give it, is to make it such that it's complete. So hopefully, eventually, we'll have laboratories that will touch on the tasking side. Okay. So if we see the evolution of OpenMP, the OpenMP at the beginning, they were only focusing on creating parallel regions, meaning creating parts of the code that were executed by multiple actors, and how to coordinate the work within those parallel regions. As we move towards 3.0, we start seeing that tasking mechanisms are started to be included. And as we go to 5.4.0, 4.5, 5.0, 5.1, 5.2, and 6.0 in a year or two, we're going to see that the focus of these implementations are more on the offloading mechanisms, the fact that our architectures are now going to be heterogeneous, the fact that we are going to have the possibility of implementing multiple variants of the same function such that it is implemented in the best way for the particular architecture. So all these tuning mechanisms that the user can actually use to be able to improve the execution of code, given the fact that we have extreme parallelism, that we have extreme heterogeneous systems. Okay. So what is actually, I have been talking about parallelism, I have been talking about heterogeneity and all this. What is actually threads and multi-threading, right? So I know everyone hears about this everywhere when they buy computers and things like that, but not everyone knows really what that means, okay? So a thread is like a worker. A thread is a particular piece of hardware that is able to execute instruction. And it is somewhat independent when it executes instructions. So you give that worker a set of instructions, which is going to be a program, and that worker is going to be executing those instructions likely one at a time, and is going to be using the instructions to be able to communicate with other workers. Okay, so when we talk about hardware threads, we are talking about the capacity of each of the cores in the system, the die that you buy, being able to execute an independent set of instructions or an independent program from the other hardware threads, right? When we are talking about software threads, we are talking about how the operating system provides the applications the ability to create these workers. So a thread can interact with memory the same way that a sequential program interacts with variables. A thread can interact with other threads, mostly through memory, although there are some other mechanisms that can be used to interact, to make the interaction between multiple threads. And also, most of the time, when we talk about a thread, we are talking about sequential execution of instructions. So when we are thinking of how do we execute programs in threads, what we are thinking is how do we give the thread the sequence of instructions that that particular thread has to execute. When we talk about multi-threading, we now have a little bit more of an issue, because the problem is that all these workers are going to be working on resources that are going to be shared. Example of shared resources are memory, but they can also be file systems, they can also be network, and they can also be other resources in the system. So one of the most challenging aspects of multi-threaded programming is that because now we are aware, we have the issue of the coordination of resources, then we as programmers are most of the time, when we program in parallel, are most of the time responsible for the coordination or for when exactly those different workers communicate, how do they use the different resources, and what are the set of instructions that each of the workers create, right? So there are three really big questions when we think of parallelism. The first one is how to create workers, right? Like, how do I say how many of those workers do I want to have? The second one is how do I assign work to those workers? And the third one is how do I make those workers communicate? And if they're going to be communicating through memory, then how to guarantee that the order in which those operations in memory happen in the order that I want them to happen, okay? So a lot of times we learn parallelism, but we never think that every single time that we are working in parallel, we are actually trying to respond to either one of these questions or a set of these questions. Okay, so one part that is kind of like interesting to me is that most of the ways that we do parallel programming right now will require the programmer to think about these three questions, which were questions that were not there before, and such new burden to the programmer has made parallel programming a little bit more challenging and difficult in comparison to sequential programming. Okay. Okay, so let's go back to OpenMP and let's think a little bit about this history of OpenMP. And OpenMP is mostly known for something called the fork join model. Okay, so we know before programs were sequential, and so the operating system will create a single program. You were able to get that program in the order in which you wrote the program, and then you knew when the program began and when the program ended. The first step that they took towards parallelism was allowing the program to obtain multiple threads that were communicating with the same shared memory. So the fork join model says that at a specific moment in the program, you are sequential. So that will be this part on the left. And then at a specific moment in the program, you are going to spawn or create multiple threads that are going to become your workers. Then once that parallel region ends, you're going to go back to sequential. And then you can do that over and over, meaning that you are forking the sequential thread that you have and then joining the sequential thread that you have. OpenMP is not a fork join model anymore, or a pure fork join model anymore, but the fork join model is still a really big part of OpenMP, and it is going to be a really big part of the GPU programming as well. Okay. So when we are talking about the fork join model, what we do with OpenMP is we annotate our code in such a way that we know how many workers are created, right? So when in OpenMP, when we say something like pragma OMP parallel, the question we are trying to answer is how to create the workers and how many workers do I want to create, right? So in this case, if I have a parallel directive like the one on top, what I will be doing is I will be creating n threads. And because I'm not specifying how many threads I'm creating, then it is up to the operating system, sorry, to the compiler or the runtime system to determine how many threads I actually create. Or even the user can determine that during the execution of the program through the use of environmental variables. If any of these questions are not familiar to you, please feel free to raise your hand, say, I don't understand what you're saying. Really, I want this to be, I know this is challenging because we are in a moment, in a world where everything is virtual, but I want this to be as interactive as possible. Okay. So as I said before, we are trying to always answer three questions: how to create threads, how to assign work to threads, and how to communicate threads. So the parallel directive, what it was doing was creating the workers, right? How to create the workers. Now, there are going to be directives that are going to be specifying particular segments of work to be executed by certain workers. So in the case of pragma OMP master, for those of you that have done this before, pragma OMP master takes one single thread that is called the thread master and will assign a piece of work to that particular single thread. So I'm identifying that here by this bold line that I have on the top right. And if you look at the purple lines, these workers are actually not doing anything. So when we start here this program, we are forking the threads, we are creating new workers. All the workers are going to be printing the high from the number of the thread, but only a single master worker is going to be printing this only once, right? So again, we are always trying to say how to create workers, how many workers do I create, and then how do I assign work to that? And in this case, how do I assign work to the master thread? Okay, so again, software parallelism versus hardware parallelism. In reality, the hardware has always been really constrained, and the operating system has always tried to make the hardware look like an infinity set of elements, right? So if you think, for example, on virtual memory is the capacity of the operating system to use multiple programs at the same time, where each of the processes that are running on the operating system has their own virtual address space. The idea of virtual memory is that the process believes that it is owner of the whole system and that it owns a address space that is quote unquote infinite for the process itself, right? So in terms of the virtual address space, I can always spawn way more memory than I can always allocate way more memory that I have in the system. Of course, there is going to be an implication in performance, but it is allowed to do that, right? So the idea of software threads is a similar idea, where we have a constraints of how many cores we actually have in the system, but the software is telling us, or the operating system is telling us, don't worry, just give me the threads that you want, or just request the threads that you want, and I will guarantee through the use of an scaling mechanism, I will guarantee that each thread gets a fair moment of execution in the cores that I have. That being said, if I oversubscribe my threads, meaning if I create way more many threads that I actually use in the system, especially when those threads are always busy doing some computation, then that means that the performance of the application is going to be hurt by the fact that I have to always be switching in between one thread and the other. So the hardware threads corresponds to the actual physical hardware that I have available, while the software threads corresponds to an abstraction that is placed on top of the operating system to be able to create those. Do we have a question? No. Okay. Thanks, Aurelio. Okay, so in this case, we may have multiple workers, each of them assigned to a different work, but in the case of the operating system, there is a mechanism that is called the scheduler that will select certain workers at a specific moment of time and will assign those workers to each of the cores. Then it will change the workers that are selected and it will continue to do this over and over. So when we think about operating system threads, there is a standardized version of the structure of that operating system thread. And more often than not, you're going to be hearing about pthreads or POSIX threads, which is often the standard that the operating system will support in order for you to be able to create the threads, right? So a pthread library will allow you to create threads that follow the POSIX standard, that the structure of those threads is going to be determined by the standard itself. The operating system is going to have a way of scaling those threads into different hardware threads. Okay, so far so good. Any questions? All right. Now, all this part so far has been about creation of works and a little bit about distribution of works in the different threads. But there is a big part that is operating. When we talk about threads in the operating system in a single process, we are saying that all those threads in that process are going to be able to access the shared memory, meaning that all of them are able to execute code that will read and write to the memory, and all of them are going to be able to observe that code, right? So if we are programmers and we are trying to implement something like this code on the right, where we have a variable called I, we assign the variable I equal to 5, and we have a variable called K, and we make K equal to I plus 5. As programmers, what we are expecting to see is that there is a memory location in DRAM that is called I, and there is a memory location in DRAM that is called K. And by some magic, we are going to get the value of I, and we are going to put it into the CPU, and we are going to add 5 to it, and then we're going to store that value of K. So in reality, what's happening is that the hardware mechanisms need to have all this complex memory organization and memory orchestration that makes this process on the right a little bit more complex than that. So on one side, we have threads have to be able to communicate with shared memory. But on the other side, we thought that shared memory was this monolithic idea of what memory is. But in reality, the hardware is so complex that shared memory actually becomes multiple memory locations. And I may have some location of K that may be falling into one of the caches, or it may be falling in DRAM, right? So because I have the possibility of having, for a single memory, for a single variable called I have the possibility of having multiple memory locations in the system, then the process of orchestrating and organizing the communication between the different threads becomes a little bit more complicated than that. So let's just think about registers. Has anybody here does anybody here doesn't know what a register is? I want to know if I should, yeah.
I don't know what are those.
Thank you. Thank you so much. Okay, so CPUs, they have operations that are like addition, multiplication, subtraction. Most of the elements that you see in a computer eventually go down to simple numbers and addition and operations. And arithmetic operations, addition, multiplication, subtraction, division, and all this. Now, the problem is that if we do those operations directly on memory, and when I'm talking about we do those operations, I mean there is an instruction that accesses those operands and tries to do an addition. If we try to do those operations directly to memory, it's going to be really costly, because every time we go, which is what I was saying before, right? We were thinking that here we're getting the value of I, we want that value to be in memory. But if we do this operation always from memory, the cost of always accessing DRAM is going to be prohibitively expensive. So registers are this local and private location within the CPU where we fetch the value from DRAM, we put it into the register first, and then we do the operations on the register. And that way, we guarantee that the memory access time in between so at the moment that I do the addition, the memory access time to the registers is always going to be within the same cycle, versus having a reference to memory that will take several cycles to do so. That doesn't mean that there are not architectures that allow you to do memory access operations. That is possible, but more often than not, you rely on registers to be able to guarantee that you do not always go and fetch values from memory. Right, so again, we're going from this really monolithic view of the system to a realistic view of the system where we may have the variable I be allocated within one of the registers. And I'm going to try to explain how this is problematic here, because if we are trying to execute a code here where we say I equal to 5 and then k equal to I plus 5, and then we want another worker to be able to say k equal to I plus 5 again, but I and k are living in the register, in the private registers of one of the CPUs, then one can see how it is not possible to right away communicate one and the other. So we'll see this a lot, where when we are doing parallelism in computers, a lot of the programs that we are, sorry, a lot of the problems that we are facing are in the coordination of memory, especially when we are dealing with shared memory, because shared memory is not really this monolithic view that we think of when we program Python or when we program any programming language. Shared memory actually has this really complex orchestration and organization that makes it a little bit more challenging. And we'll see that in other architectures that are not CPUs, people are starting to explore other ideas where we do not rely on caches, we do not rely on mechanisms to guarantee that the order of operations are fixed and such. So that makes it even harder for the programmer, because the programmer has to not only think about what memory is going to use, but also where the memory is going to be living. Right? Is that, Julian, is that a little bit more clear?
Yes, thank you.
Mm-hmm. Excellent. Okay, so now let's take a little bit, let's try to make our thread abstraction a little bit more complex. We now know that the thread is going to have some access to a shared memory. When I say thread, I'm talking to the workers here, right? And we know that the thread is going to be accessing some private memory. It may be in the form of a register, but it may also be in the form of a section of memory in the system that is going to be different in between the shared in between one thread and the other. We'll see later on when we talk about OpenMP, and especially in the lab number 1, that we have the ability to specify if a variable is going to be living in the shared memory or if a variable is going to be living in the private memory. And there are going to be implications of each of those elements once we put it into the program. Okay. So before we get there, let me introduce some concepts that are important here. If I have a memory location here, right, that is going to be shared in between the different workers, I need to be able to determine how that memory location gets access. Because I already mentioned before, each thread can start putting values or data in their local registers that makes it hard for the program to be able to coordinate memory access to variables that from the programmer's perspective, they were supposed to be living only in shared memory, right? So OpenMP, what it does is it gives us a set of tools that allows us to coordinate the access to that particular memory. Okay, so this is pretty much the same thing that we have here. It's just that I'm putting it on top of the fork-join model. And what we are seeing here is that we have some region in green, some region in green that I'm calling the global shared memory, and some region in blue that I'm calling the thread local memory, right? The global shared memory is going to be seen by all the threads, while the local memory is only going to be seen by the particular thread I have there, okay? So one operation that we can do in order to be able, before I get there. So one thing that we have to do in order to be able to specify a memory location that goes into a fork-join model is we need to specify if we want that memory location to be shared across the different threads or if it's going to be private for each of the different threads. And if it's going to be private, that means that we are going to be making copies of each of those. Am I correct to say that the reason why we have a registered private memory is because it is faster for threads to access private memory than shared memory? So yes and no. Okay, so private memory, so registers are private memory for the thread, but it is not the only private memory that a thread may have. A thread may have private memory that lives in DRAM, and in that case, it doesn't necessarily mean that it's going to be faster. right? So yes, it is correct that the reason why we have registers is because we want the CPU to be able to perform operations as fast as possible. And so we are going to be using registers to keep some operation or some data, like partial results in the case of an arithmetic operations that have multiple operands, a plus b plus c plus d. Then we want to be able to keep the data of intermediate results around in the register such that the access to the next operations are going to be faster. So yes, the idea of registers is to increase performance in the CPU by reducing the memory access time to those registers. Now, private memory can be in the DRAM as well, so the memory access time to DRAM can also be extended. There are certain implications here, right? Yeah, exactly. So register is not the only private memory, exactly. So in this case, for example, when I say thread local, I don't mean the registers. I also mean, it can also be the registers, but I also mean that there are going to be memories, like memory regions that are going to be only accessed by that particular thread. Exactly. You're right, Carlos. That is exactly right. Okay. So when I say a memory location X is going to be shared, I mean that every single memory reference that I get to X is going to be always fetching that particular memory location. When I say that it's going to be private, I mean that every single memory location of X is going to be independent and is going to be private for each thread. And I have an example of that. Okay. So in this case, if I have a variable that is called int X equal 5 and I make it shared, then when I print that variable from any of the threads, I'm able to print this value 5 because we are always accessing the same memory location. What happens here is that because we know that memory or like the memory organization of the system is complex, and because we know the possibility of having that variable X in a register, for example, or reading and writing into that variable and operating over that variable may be different instructions by themselves, then we do need certain operations that we call atomic operations that are guaranteed that the access to the memory from the read to the operation to the write happens in a single, as if it were in a single cycle, right? As if there is no other operation happening in between. I do have some examples in the lab for this, but just so you understand here, what would happen if the read operation of all the threads happens first, then all of the threads increment the 0 by 1, and then the write operation happens at the end. The X is going to be equal to 1, right? But if we look at this code, what we wanted was that each of the parallel threads would be incrementing the X by 1. So we wanted the X to be equal to the number of threads. So in this case, if we do not use atomic operations, there is this possibility of a certain different organization of instructions in the system that will lead to what we usually refer to as a data race. That is the fact that we expected a memory operation to have a specific value, but then due to the different ways or the different instructions happening at different times, we may end up with a different value that is not the one that we have. Yes, I cannot always explain that. So memory, in this case, memory X is a memory that is shared in the system, right? So when we think of something like I++, what do we need to do? We need to do a load operation, an increment operation, and a store operation. The load operation is going to be copying the value from the global memory into the register. The increment operation is going to be taking that register and incrementing it by 1. And the store operation is going to be sending the result of that operation back into memory. So when I don't do an atomic operation, all those 3 operations are independent from each other. What happens is that this here can be loaded by this thread, right? Then this thread is going to be looking at a 0. Then this here can be loaded again by the second thread because the 2 threads are independent from each other, right? So they are not communicating saying, hey, I already did the instruction that is called load. They are just loading instructions, right? So both of them are going to have in their registers a value of 0. And when they do +1, both of them are going to get a 1, right? And then this is the result that they're going to try to store. So we are going to store a 1 here, and then we are going to store a second 1 here, right? So just because the load operation and store, the three instructions, load operation and store happen independently, there is the possibility of having other load operations or other store operations in between my single set of instructions in my thread. So when I say atomic, I guarantee that all those three operations, load, increment, and store, happen atomically, meaning there is no other instruction in the system that is executed in between those three. Does that make sense? So I have an animation here that is, I take, yeah, thread one is going to read from X, is going to increment it, and then it's going to store it, and it's going to change it to 1. Thread 2 is going to read from X, or thread 3 in this case is going to read from X, is going to change it, and then it's going to store it, and it's going to make it a 2. So each of those three operations, load, increment, and store, happen without any interruption of any other threads. So it has to be something like what I'm trying to explain here is it has to be the three operations at the same time: read, store, read, increment, store. All of the three operations have to happen at the same time. Does that make sense, Gideon? Okay, perfect. So that is what we call atomic operations. Okay, before we said that we could also specify memories that were private. So 2 examples ago, we had, because I have to do this really quick. We had the variable X that was shared, right? And we knew that whenever we printed that X value, it was going to be the same for everyone because the access to that variable was going to be always the same. Then when we say private, what we do is we guarantee that each thread has its own copy of X. Now, here is the trick. How many of you know what pointers are? Or let me say it differently. How many of you doesn't know what pointers are? I think this concept of pointers is important for this case. Okay, every single variable that we have in a program have to be stored somewhere in memory. But memory is like this shelf where each of the locations in that shelf has a number which corresponds to that particular memory location, what we call the address of the memory location. A pointer is the value, the number that represents that particular memory location, and it is associated to a type that usually represents how big my memory location is, right? Integers are going to be 4 bytes, doubles are going to be 8 bytes, things like that. So when we are talking about privatizing variables, what we are doing is we are assigning a different number to that particular memory location. So that means that if this memory location has the location 0xf, this memory location may have the location 0xa, and this one can be 0xt, and this one can be 0xfff, right? So each of these memory locations that represent X in the program are going to be stored in different locations of that shelf example that I was trying to make it, right? So the privatization of variables only guarantees that any single access to that variable within the parallel region is going to have its own independent local memory. And that's what I was saying earlier, that local memory doesn't always point to the registers. It can also be pointing to a DRAM location. It's just that the DRAM location is only accessible by the particular thread. A pointer is a special kind of variable that is used to store the memory address of other variables. Exactly. That is right, Carlos. Okay, you will see in lab 1 that I use pointers a lot to try to explain these concepts, and you're going to be printing those memory locations, and they're going to be looking ugly because it's going to be a really big number, but you're going to be able to see how each of those memory locations in a private region is going to be different than the shared memory location. Okay. First, private. As I say earlier, privatization only guarantees that you have a different memory location, but that memory location doesn't have to have the same value that you had at the beginning of the private region. First, private guarantees that not only you have your own memory location, you also guarantee that that memory location gets initialized by the value that the original variable had prior to the parallel region. Okay, So the difference here is only the fact that we are initializing the new memory location with the value of X. So if we do a print here, we don't know what value we are going to get because it may depend by whatever trash there was in the memory before. But if we get here, we do know that the value of X is going to be not only allocated for each thread, but also initialized by each thread to the value of 5. Right? So it guarantees privatization, but it also guarantees values. Okay, there is also the problem that we have is that when we do privatization of memory, what happens when we want to go back into the program and say, what is the value of X, right? Because here, what we were doing was creating a new value of X per thread. So we had an X here that was global, but here we have an X that is valid for each of the threads. Now, if we were to modify each of those value of X, how do we go make an agreement of what would be the value of X after the fork join operations happen, right? Like at the end of this join operation, which one of these values that we have, the different values of X that we have in memory, is going to be the valid one? And there are different ways that we can do that. One of them is that if we assume that we have a loop, we are going to take the value of X that is contained in the latest loop iteration, right? So if we are going, for example, from 0 to 10, and each of the iterations is going to be modifying the value of X, then only the last iteration is going to be copied over from here into the original memory location at the end of the fork join region. Okay. Then if we have something that is called here, there you go. If we have something that is called a reduction is an operation that we perform on all the different private versions of the memory, and we specify what is the operation that we are going to apply in order to combine all those memory locations into a single memory location. So a reduction, what it does is combining all the different private memory locations of each of the threads, given a particular operation. In this case, it's going to be an addition operation, and then it's going to combine all of them into a single value that is going to have the added value of each of the memory locations. So if we had a memory location that had the value of X equal to 5, and we made a reduction, then we assigned I to each of the reductions, then we end up with something like n times n minus 1 divided by 2, which is equal to the sum of I from 0 to n, right? Does that make sense? Okay, I'm going to assume that that is a yes. Okay. So if you look at all this, all we are trying to answer is how do we coordinate and communicate the workers, right? We were thinking how to create the workers before with the parallel regions. Then we thought about how to assign work. We gave an example with the master directive where we were assigning work to only a single one. And later on, we started thinking about memory, and we started thinking about how do we coordinate operations with memory. So what we are saying here is, if we have all these workers and all of these workers are working on a shared resource, how do we coordinate that shared resource in a way that we can think about what would be the potential value of that shared resource? So again, those three questions are going to be always really important when you program in Python. Okay, just a little bit of an introduction to OpenMP syntax, such that you can go to lab 1 and play with all these concepts. So the first thing is that we're going to use something called pragmas. Pragmas are annotations to the code that allows the compiler to take a look at the code and say, for this particular section of code, I'm going to be transforming my code from this original structure to that original structure. So what you see is that a lot of the times in OpenMP code, what you would have is pragma, the hashtag sign, the pound sign, whatever you want to call it, followed by the word pragma, followed by the word OpenMP, or sorry, OMP, corresponding to OpenMP, followed by the different directives or clauses that we are going to be using. So what we are doing with a directive is just telling the program, the compiler, that we are going to be using OpenMP, that particular region, and that we want the code to be transformed based on the semantics of that particular directive. Right? So there are some differences here. A directive is a base language mechanism, meaning a word that is saved by OpenMP that will specify a particular program behavior. A clause is an optional modifier to a directive. So we have, for example, parallel region, and we can modify the parallel region by saying how many threads we want to create with the clause non-threads. Do the reduction applies to any binary operation or primitive operation. So there is, originally there was only support for primitive operations. There is a new version of OpenMP that supports it supports that you declare, reduction operations, right? So you specify what the code is for whatever variable you have. Or you can also rely on basic operations and then overload those basic operations into C++ overload mechanisms that allows you to specify how the addition happens and whatnot, right? So right now you should be able to, it depends on how the maturity of the program of the compilers are, you should be able to create your own reduction operations, okay? When I say based on the maturity of the compilers, is because the declared reduction is relatively new, it's like 2 or 3 years old. So it takes a while for compilers to catch up with the specification, and sometimes you'll see that compilers do not have all the features implemented right away. Okay. Oh, okay. So we had directive, we have the clause, and we had a construct that it becomes an OpenMP executable directive. An example of a construct was the parallel region, because once we face a parallel region, we have to execute. Oh, by the way, Isaac, did I answer your question? Okay, thank you. Okay, so an example of a construct is the parallel construct, because every time we see a parallel region, we know we have to execute code in order to make that happen. So not every directive is going to be a construct. There are directives that are just going to give information to the compiler. We're not going to explain them here, but there is one, for example, that is called requires, that is telling the compiler that the particular code requires a specific feature in order to work. So that is something that it never gets executed. It is just living there, right? It may have some clauses to modify them, but it doesn't really specify something that is executable during runtime. So the constructs is something that is executable, while the directive can be just a word that may or may not be a construct. So this is an example. Pragma OMP, we are just telling the compiler we're going to use OpenMP. Then we have the directive that is the combination of Pragma OMP parallel non-threads. We have a clause that is modifying the number of threads that we are creating, and we have a construct because we know that the parallel construct is going to end up executing something that will create the threads. So OpenMP, as I said, is not a programming language. Should have changed the name of this slide. I'll fix it later. So OpenMP is not a programming language, right? OpenMP is an extension to a programming language. That means that all the different compilers, I'll explain that in a second. All the different compilers that you have in that are able to execute, to compile C, C++, and Fortran, they may or may not support OpenMP. But there is a really, really long list of a lot of compilers that support OpenMP. Not all of them support the complete set of OpenMP. Some of them stop at a specific version. So they say, I support OpenMP 3.0, meaning that I can do tasking, I can do parallel regions, but I cannot do offloading. And they are always trying to catch up with the different features that they have in OpenMP. More often than not, if you go for the latest version of OpenMP, you're going to have a really hard time finding compilers that support all the features of in the latest version. So we are talking about version 5.2, which is the latest one right now. If you try to look for compilers that support 5.2, I'm going to be bold, but I don't think that there is any one compiler that supports the whole 5.0 specifications. Okay, so we had a comment by Dawson that says, I think you can only use reductions with associative operations, division season, right? So that is correct, because otherwise the result will not necessarily be correct because the ordering of the operations. That is absolutely right, Dawson. And funnily enough, the operation minus was supported by OpenMP until I think version 5 or 5.1. So 20 years after, they realized that it made no sense to have a reduction with the minus operation. So this is absolutely right. It has to be an operation that you can change the order, okay? So correct, usually reduction operations are implied in a tree-like manner. That is correct, and do not take into account non-commutative operations. Yes, Carlos, there is a paper by Johannes Dorfert on reduction operations, and he talks about different possible implementations for reductions. One of them is the tree-like, the other one is atomic, and there are other ways that you can actually do reductions. So if you want to read more about that, let me know and I will share the paper with you. Okay, so what does the compiler actually do? We take a program that has OpenMP annotations, we give it to a compiler. What the compiler is actually doing is taking the program, analyzing it, and it's going to add a lot of other code that we are going to call the runtime. Okay, I'll share it with you. That I'm going to call the runtime. Okay, the runtime is an additional code that is written by the compiler people that contains all the logic to create the threads, communicate the threads. So the compiler, what it's doing is connecting the code from the user to the runtime function calls and kind of like putting one and one together. So the simplest example that I have for you is pragma-OMP parallel 4 will be transformed to a function called that in LLVM is called KMPC parallel. That function will eventually call pthreads that will eventually create the different threads. So in reality, the function may or may not call pthreads because there are optimizations to create the threads prior to the parallel region. Doesn't matter, it's completely transparent to the user. What is important here is to understand that the OpenMP implementations are going to be adding all this gigantic piece of code, that the purpose of that code is to be able to connect the semantics of the parallelism, meaning the meaning of the different directives that we have in OpenMP, with the actual behavior of those directives in the particular hardware that we have. And that is what we call the runtime. This slide is just so you know that when you debug OpenMP code and you try to look into the traces, you're going to start seeing a lot of other functions that you did not write in the first place. Those functions are most likely going to be corresponding to the runtime system. The other thing is important to know that we have a runtime system. So there is this piece of code that is doing the glue logic in between what we want to do with the semantics of the OpenMP code and what we want and what the program has to do with the limitations of the particular the particular hardware where we are executing the OpenMP program. Okay, so just keep that in mind. So how do they actually do this? There is this process called function outlining. How many of you have heard of function inlining? You can use a reaction, a thumb up, or something like that. No? Okay, good. Thank you, David. Excellent. So, okay, function inlining is when you take a function in your code and the compiler takes that function and copy and paste it directly into the place where you call the function. And the reason why they tend to do that is because during function inlining, you guarantee that you don't have to do a jump operation out of your function. You increase the scope of the variables in such a manner that you can actually increase the optimization opportunities in that code. What happens in OpenMP is that we do the contrary. We do function outlining, meaning that we had a piece of code that was inline into the code that we wrote. And by putting OpenMP, the compiler is actually creating an outline function with a runtime function that will call the outline function. This is really, really important because in a lot of OpenMP implementations, what you will see is that if you try to run the same program with OpenMP enabled, sequentially, the performance is going to be absolutely terrible. And the only reason is because the compiler is purposely removing code from your function, putting it into a second function. And when it does that, it loses the opportunity to perform optimizations between one and the other. There is yet another paper by Johannes Dorfert. I feel like I'm talking about only Johannes, but I know his work really well, that teaches the compiler how to understand these functions such that the optimizations can cross from one to the other. But that paper highlights that the fact that during the outlining process, a lot of the performance can be lost. So when we do parallelism, we gain a lot of performance, but the whole outlining process mechanism can hurt us if we are not using a compiler that is aware of this particular function calls. So the compiler implementation that you use is absolutely important for the execution of the code. So function outlining is a process that happens over and over in OpenMP. It's just so you understand that whenever you have certain directives, those directives are going to become transformed into other functions that you did not write, that whenever you look at the traces of the execution of your code, they may have some information of where the directive comes, sorry, where the function comes from, but the name of the function is not going to be familiar to you because it's going to be given by you by the programming, by the compiler itself. Okay. And so this is just to say that we do function outlining and we insert runtime calls to be able to support OpenMP. Okay. I'm going to stop here. And I'm going to give you the opportunity